We've been talking about transformations. Translations slide, reflections flip, rotations turn, and dilations change the size of an object. So today what we're going to do is basically put all of that together so that it's several of those on one object. So when two or more transformations are combined to form a single transformation, the result is called a composition. Just like when you write a composition, you put a bunch of words together to form a single thought or a single idea, then that is what happens when we put two or more transformations together. It's a composition. And so we want to talk about, we're going to go like from our original pre-image, and then we're going to do our image, but then what we're going to do is we're going to change our image. So we have our pre-image A, we have our A changed, and then we have our A changed. So let's look first at this one. ABC is shown on the coordinate plane. Find the coordinates of the vertices of A. This should be double prime, and double prime. After a reflection across X is equal to 0, and then a reflection across Y is equal to 0. So first we're going to do X is equal to 0. So if you remember, X is equal to 0 means you're going to draw a line that goes through X at 0, which just so happens to be the y-axis. So remember, when you reflect, you can do this on a graph or you can use the rules. Remember, when you reflect across a y-axis, your rule is that your x values are going to change because you're moving horizontally. So my original A point was at 2, 1, and I always recommend writing those points out so that you have the numbers already done. You only have to think of it once. There's lots of room to make mistakes on these kinds of problems, and you don't want remembering something wrong or reading it incorrectly off the graph because you've looked back at it 4 or 5 times and getting it wrong that way. So just write it down so that then you don't make that mistake. So we're going to reflect across X is equal to 0, which is the y-axis, which means we're going to flip over this way. Now so we know that our X values are going to change. So that positive 2 becomes a negative 2. That positive 6 becomes a negative 6. And that positive 4 becomes a negative 4. Now I can do a quick double check. All of those points were in quadrant 1. They flipped over that green line and went into quadrant 2. And all the signs in quadrant 2 are negative positive. And so all of my points should match that. Now from there, I want to change that. Now when I do that, I'm going to do the next thing. I'm going to reflect across Y is equal to 0. So I'm going to draw a line through the y-axis at 0, which corresponds with my x-axis. So now I've moved everything over. Now I'm over here because I flipped it over, and now I'm over here in quadrant 2. So now I'm going to flip it over that orange line. Think Foursquare. You're standing in there in that green circle, and you're going to push it across into quadrant 3. So you're going to go across that orange line. And so now we know, because we're flipping across the horizontal line, that we're making a vertical change, and that rule is that your xy's become, the x stays the same and the y changes. So the x stays the same, right? We went from here to here, now we're going from here to here, and then the y values change. The x value stays the same and the y values change. The x value stays the same and the y values change. Now, that also makes sense if you look, because I was in quadrant 2 on that middle step. I was in quadrant 2 and I flipped over and I went into quadrant 3. And in quadrant 3, all of my signs are negative, negative. So what single transformation would have given you the same result? So some people would think that y equals negative x would give you the same result. But remember, with y equals negative x, you have to switch the x and the y values. So that wouldn't work, because notice that all of my x and y values stay the same. But what you could do is you could do a 180-degree rotation. And it doesn't matter which direction, counterclockwise or clockwise, because either way you would turn from the original quadrant 1 and into quadrant 3 when you're done. So if we look at this, the vertices of PQR, and I'm going to write those down again just because I like to have them right there so that everything is stacked up. It helps me to keep everything straight. I want to translate I'm going to follow this rule right here. I'm going to translate x minus 6, there should be an arrow right there, x minus 6, y. So that means all of your x values are going to decrease by 6 and your y values are going to stay the same. So we just go in, we decrease our x value by 6. 2 minus 6 is negative 4. Your y value stays the same. You decrease negative 4 by 6 and you get negative 10 and your y value stays the same. And then your x value, negative 3, decreases by 6, and it gives you negative 9, and then the negative 3 stays the same. So that slid down. So you can imagine what that triangle looked like. It slid down. Then you're going to reflect it across the x-axis. Okay, so remember when you reflect across the x-axis, you have a vertical change, and so that means your xy is going to become x negative y. So now I go from my original, my pre-image to my image, and then I change that image again. Your x value stays the same, and your y values change. Your x value stays the same, and your y values change. Your x value stays the same, and your y values change. Okay, this is called, this motion is called a glide reflection because a translation is a slide or a glide. And so think you're sliding down the hall and then you catch your sock on something and you flip over. That's a glide reflection. So if we look at 3, the endpoints of M are at negative 2, 1, and N is at 3, 4. We're going to reflect about the line or in the line, y is equal to x. Well, remember that gives you the hint about what you're supposed to do. Your xy will become, it says y is equal to x, so your y value is your x and your x value is your y, because if y is equal to x, then x is equal to y. So then we're going to switch our 2 points. So if I write my coordinate, my y value becomes my x, that was negative 2. My x value becomes my y, which was 1. For n, my y value becomes my x, which was 3, and my x value becomes my y, which was 4. So there's my new points. Now remember with rotations we have that little trick. You can use the rules or you can use the trick. I'm going to use the trick because it's so much easier. So we can put our points over here. So M, remember we just need to know where it starts. M prime starts in quadrant 4 and N prime starts in quadrant 1. And so remember we do switch and then we switch back, or we keep the letters the same. Switch, same, and then we name where it came from. So we just take the numbers. When it travels, when it rotates, it's like it's traveling, it takes no luggage. We're going to name it. We're going to get what we need when we get there. And so we'll get the signs from the quadrant that it's in when we get there. So we're going to rotate 180 degrees. So we're going to switch our x and y variables. We're going to switch those coordinates every 90 degrees. So M is going to switch when it goes to quadrant 1, and it's going to switch back or go back to being the same when it hits quadrant 2. So the order that I write my letters in, or my numbers, is going to be the same. Notice I did not write the negative. I don't care about that until right now. Okay, when I rotated around, I went quadrant 1, quadrant 2. Well, the signs in quadrant 2 are negative, positive, so I have to make those coordinates match. Now N is going to do the same thing. It has to move the same distance, right? So it's going to move 1 quadrant, 2 quadrants. It's going to switch and then go back to being the same. So they're going to be in the same order that they were originally. And then I'm going to name it based on where it landed. So it landed in quadrant 3 where everything is negative, negative, and so I change my signs so that they are all negative, negative. Now in this particular case, it asks, would you get the same result if you performed the rotation first? Yes, in this case you would. Now that's not the case with every single composition. Some of them are affected by the order. For instance, this next one. And the main reason that we have this next one is for you to see the notation too. This is composition notation, and it's this big circle here in the middle. And why that's important is because when you have that big circle here in the middle between the two, you're going to do this transformation first, and then you're going to do the dilation. Because the dilation is the result of, it uses the results of what happens with the transformation. That's just how compositions are written. And so we have our A at negative 4, 4, our B at -4, 1, and our C at -1, 2. So remember that this notation for the translation means I'm going to go forward, I'm going to go to the right 5, and then I'm not going to go up at all, so my Y values are not going to change. So my X values are going to increase by 5, so -4 plus 5 is 1, 4. -4 plus 5 is 1, 1, and -1 plus 5 is 4, 2. So that's the translation. Then I'm going to do the dilation. This is a dilation of a scale factor of 2. So now I'm going to double that image. So 1 times 2, 4 times 2. Okay. So the question is, does the order matter? Well, I already alluded to that. So if I were to do this in the opposite order, let me show you what happens. My A was at -4, 4. My B was at -4, 1. And my C is at -1, 2. If I dilate it first, because remember we go in the opposite order when it's written in this notation. Only when it's written in this notation. Only when you see that dot do you do this. Notice every other time I did it in the order that it was written in the problem. This dot is the only reason that we're doing things backwards. So if I dilate it, this time I'm going to dilate it first. So I dilate it by a factor of 2. You can see now I'm moving a much bigger triangle. That's why it affects what's going on so much. Now I'm going to translate it to the right 5. -8 plus 5 is -3. Same thing here. And then -2 plus 5 is 3, 4. So you can see that these two are very different. They created different results, and it's because of that dilation that happens. So whenever you have multiple transformations in the same problem, it is considered a composition. Unless you have it written in this notation right here that we just talked about, you do it in the order that it's written. Some of the time it doesn't matter, but sometimes it does. So just do it in the way that it's written, and